Hello friends, I Deepak Prajapati welcome you in lecture number 7 on partial differential equations. So today we are going to discuss third type of solving Lagrange auxiliary equations. In earlier two lectures we have discussed two types of solving Lagrange auxiliary equations. So if you have not watched those two lectures, you can refer those two lectures before watching this lecture. So in this type 3 we are going to use one principle of algebra. So what is that principle that we first discuss? So if we have these three fractions are equal, for example here three equal fractions are there, dx upon p equal to dy upon q equal to dz upon r. So if fractions are equal, then if we multiply this first fraction by p1 in the numerator as well as in the denominator. Similarly, suppose we multiply second fraction by multiplier q1 and third fraction by r1, and if we take their linear combination, then we will have this new fraction p1 into dx plus q1 into dy plus r1 into dz divided by p1 into p plus q1 into q plus r1 into r. So using these three multipliers p1, q1, r1, we have generated new fraction. So principle of algebra says that if we choose multipliers in this way and if we generate the new fraction, then this new generated fraction is also equal to all these three fractions. So using this principle of algebra, by selecting appropriate multipliers, we can generate the new fraction which is equal to given equal fractions. Now suppose these multipliers p1, q1, r1 are selected in such a way that this denominator becomes 0, then we can write this numerator equal to 0. We have discussed in earlier lecture that if in equal fractions denominator of some fraction becomes 0, then numerator of that fraction can be equated to 0. So if we are able to find out multipliers p1, q1, r1 such that this denominator p1 into p plus q1 into q plus r1 into r becomes 0, then we can put numerator equal to 0, and after integrating we are able to find out the first solution. So here I have written if p1 into p plus q1 into q plus r1 into r equal to 0, then we know that p1 dx plus q1 dy plus r1 dz equal to 0, which can be integrated to find out one of the two integrals. Similarly, we can select another set of multipliers in such a way that denominator becomes 0, and then we can find out another integral of Lagrange auxiliary equations. So this p1, q1, r1 are called multipliers. So in this lecture we are going to discuss this third type of solving Lagrange auxiliary equations. So our focus will be to select multipliers p1, q1, r1 which may be constants or functions of x, y, z, such that p1 into p plus q1 into q plus r1 into r becomes 0. So if this becomes 0, then we can say that p1 dx plus q1 dy plus r1 dz equal to 0, and which can be integrated to obtain one of the two integrals. So in this lecture we will do some examples to indicate this third type of solving Lagrange auxiliary equations. So we will be interested in finding out these multipliers. Of course we will first check whether it is possible to find out solution by directly comparing the fractions, or if one solution is possible, whether we can use that solution to obtain the second solution, and so on. So if type 1 and type 2 fails, then we will think for this third type. Sometimes we will be combining type 1 and type 3, or type 2 and type 3. So that will depend on the given problem. So we understand this with the help of this example. So you can see this is Lagrange linear quasi-linear equation. So given equation is Lagrange equation, or we can write quasi-linear equation. So as usual, we have to start with Lagrange auxiliary equations. So Lagrange auxiliary equations are dx divided by coefficient of small p, which is x into y minus z, equal to dy divided by coefficient of small q, which is y into z minus x, equal to dz divided by right hand side, which is z into x minus y. Now if you observe here, we are not able to compare any two of these three fractions. If you concentrate on first two fractions, dx and dy, then z must be absent, but you can see the presence of z here. Similarly, if you observe second and third fractions, then we have differentials dy and dz, but x must be absent, but x is present here. Similarly for dx and dz, if we wish to compare first and third fraction, then because differentials are dx and dz, y must be absent. So it is not possible to find out one solution or two solutions by directly comparing the fractions. So we will try to generate the new fraction by selecting proper multipliers. Now how to select proper multipliers? That can be decided from this denominator. Suppose here I have x into y. So here you can see, if I multiply y with this bracket, I will have minus x into y. Similarly here I have minus x into z. So you can see there is a x into z here, and here I have y into z. So you can see there will be minus y into z. That means if I add these denominators of each fractions, then I will obtain 0. So it suggests that we will select multipliers as 1, 1, 1. Okay, so choosing 1, 1, 1 as multipliers, so we will generate a new fraction. So we write in this way, choosing 1, 1, 1 as multipliers, each fraction of 1 equal to each fraction of 1 equals, so here I will consider 1 into dx plus 1 into dy plus 1 into dz, and here I have to add all these denominators. So I directly multiply with x this bracket, and I write x into y minus x into z plus y into z minus x into y plus z into x, or x into z minus y into z. So this equals, here we can write dx plus dy plus dz and you can see x into y will cancel out with minus xy, yz minus yz 0, zx minus zx 0. So we have 0 in the denominator. So therefore we can write d into x plus d into y plus d into z equal to 0. So the first solution is obtained by integrating. We get x plus y plus z equal to c1. So therefore u is nothing but x plus y plus z equal to c1. So this is the first solution or first integral of Lagrange auxiliary equations. Similarly, we have to select another set of multipliers which is independent of these selected multipliers. Another set of multipliers must not be dependent on this first set of multipliers. That means we cannot select 2, 2, 2 as multipliers. Similarly 3, 3, 3 as multipliers. So set of multipliers must be independent of each other. So for another set of multipliers, again we have to look at Lagrange auxiliary equations, and we must get the idea from these Lagrange auxiliary equations. So which set of multipliers is appropriate so that I obtain 0 in the denominator. So here you can see, if I multiply this x into y minus z by 1 by x, then x will cancel out and I will have y minus z here. And if you observe here, there is a z here and I will obtain y minus z here. So if I multiply this by 1 by y, y will cancel out and I will have z, and here I will have minus z. Similarly here I will have minus x, and if I multiply this by 1 by z, I will have x. So from this we can have the idea that the possible choice for multipliers is 1 by x, 1 by y and 1 by z. So this is just from our observation on Lagrange auxiliary equations. So by solving more and more problems, you will be able to identify the appropriate set of multipliers. There is no method or there is no general method to select the multipliers, but it will come by practice. So by doing more and more problems, you will be able to decide multipliers easily. Okay, but you have to concentrate on Lagrange auxiliary equations. So here another set of multipliers is 1 by x, 1 by y and 1 by z. So we write choosing 1 by x, 1 by y, 1 by z as multipliers. Each fraction of 1 equal to so I write here, with dx I have to multiply with 1 by x, 1 by y, 1 by z dz. And here if I multiply this denominator by 1 by x, I will have y minus z. Here I will have z minus x and x minus y. So first I write y minus z plus z minus x. Plus, so here we multiply with 1 by x, so we have y minus z. Here y will cancel out z minus x, and if we multiply this by 1 by z, z will cancel out and we have x minus y. So this reduces to 1 by x dx plus 1 by y dy plus 1 by z dz. And here you can see x will cancel out, y minus y which is 0, z minus z which is 0. So we have 0 in the denominator. So therefore we can write numerator equal to 0 as we have explained in earlier lecture. 1 by x dx plus 1 by y dy plus 1 by z dz equal to 0. And integrating we obtain integral of 1 by x with respect to x is log x. Similarly 1 by y has integral log y, and for 1 by z it is log z. And because I am having logarithm in each term, I can adjust constant as log c2. Using property of logarithm, this I can rewrite as log of xy into z, which is equal to log c2. And because log is 1 function, we can write xyz equal to c2. Therefore second solution is v equal to xyz. And as we know, the general integral or general solution is phi of uv equal to 0. Therefore phi of what is our first integral, u equal to x plus y plus z, and second integral is xy and xy into z. So x plus y plus z comma x y z equal to 0, and we have to mention what is phi. So where phi is an arbitrary function. So in this example, it is possible to find out appropriate fractions in such a way that we obtain 0 in the denominator, so that we are able to find out the integrals by direct integration. So in this way you can decide the appropriate set of multipliers and you can solve the resulting partial differential equation. So we can consider one more example. Given equation is also Lagrange equation, so we directly start with Lagrange auxiliary equations are dx divided by coefficient of small p, which is z into x plus y, dy divided by coefficient of small q, which is z into x minus y, equal to dz divided by x square plus y square. Now we have to think whether we are able to compare any two fractions. So it is not possible here. You can check. If I think for first two fractions, differentials are dx and dy, so z must be absent. So that is possible here. We can cancel out z and we can solve the resulting ordinary differential equation. So one way is one solution can be obtained by comparing fractions 1 and 2 directly. Another way is we can find out the appropriate multipliers such that we obtain 0 in the denominator. So which appropriate multipliers we have to select. So from this we may have the idea that if I consider here I have z into x, and here also I have z into x, and here I have x square. So suppose I consider here I have z into x. So if I multiply this by x, then I will have x square into z. Okay, this is the way how you can, by trial and error, select the multipliers. Suppose I concentrate here, then I have z into x. So if I multiply this by x, I will have x square z. So here you can observe there is a x square here. So you can multiply this by minus z, so that these two will cancel each other. So from this I have idea that if I multiply this by x and this by z, then I will have x square z here and I will have minus x square z here. So that will cancel each other. Similarly, if I multiply this by x, I will have second term as xyz. So I must have minus xyz somewhere. So here you can see I have z into x. So it suggests that I have to multiply this by minus y. So if I multiply this by minus y, I will have minus z by x and minus minus plus and y into y square z. And here I am multiplying with minus z, so there will be minus y square z here. So you can see we have terms which will cancel each other. So from this we can have the idea that we should select these multipliers x comma minus y comma minus z. So we will select this x minus y minus z as multipliers to obtain 0 in the denominator in the new fraction. So choosing small x minus y minus z, okay, this I will multiply with minus z as multipliers. We will have new fraction which will be equal to each fraction of equation 1. So each fraction of 1 equals x into dx minus y into dy minus z into dz. Here I multiply with x, so I have z into x square plus xyz. Here I multiply with minus y, so minus z by x or xyz minus minus plus z into y square, and here z into x square minus z into y square. So you can see terms cancel out each other. xyz is cancel out here. Z into y square minus z into y square. So this says that we obtain 0 in the denominator. So from this x into dx minus y into dy minus z into dz divided by 0. So therefore x into dx minus y into dy minus z into dz must be equal to 0. And if we integrate, we obtain x square by 2 minus y square by 2 minus z square by 2, which is equal to, we can adjust constant as c1 by 2 because there is 1 by 2 in each term. So we have x square minus y square minus z square equal to c1. So therefore first solution of Lagrange auxiliary equations is u equal to x square minus y square minus z square equal to c1. Now we think another set of multipliers which is independent of this set of multipliers. So now we have to search for another set of multipliers which is different from this. So from this you can have the idea. Here I have selected x comma minus y comma minus z. So 2 negatives and 1 positive. Now here I started by multiplying with x. Now suppose I start by multiplying with y, then what is my observation? That I check. Okay, so now suppose I multiply this by y. So I will have x, y, z, and here I will have minus z into y. So that will cancel out. Here I will have minus z into y, and here I have, if I multiply this by y, I will have x, y, z, and here I will have minus z into y. So if I multiply this by x, I will have minus x, y, z. That will cancel each other. Now here I will have, in the second term there is a y, and I am multiplying with y, so I will have z into y square. So here I have y square is there, so I must multiply this by minus z. So if I consider multiplication of this with y, I will have z into y square, so that will cancel out minus z into y square. Similarly here I will have minus x square z, and I will obtain x square z from here. So this suggests that we have to select y, x and minus z as another set of multipliers, so that we obtain 0 in the denominator. So we select that set of multipliers and we obtain the another solution, choosing y, x minus z as multipliers. Each fraction of 1 equal to so y is multiplied with dx, x is multiplied with dy minus z dz divided by y into z into x plus y. So we have xyz plus z into y square. xyz plus z into y square. Second is multiplied with x, so we will have z x square minus xyz. So plus z into x square minus xyz, and last fraction is multiplied with minus z, so it is minus x square z minus y square z. So minus x square z minus y square z. So you can see these terms cancel out each other, minus x square z plus x square z. So we obtain 0 in the denominator, and numerator is y dx plus x dy minus z dz divided by 0. Therefore y dx plus x dy minus z dz equal to 0. Now this y dx plus x dy is nothing but differential of x into y minus z into dz equal to 0, because d of x into y will be x dy plus y dx, and integrating we get integral of d of xy with respect to integral of 1 with respect to x into y is x into y minus z square by 2 equal to constant of integration, say c2, or we can rewrite this as 2xy minus z square equal to 2 into c2, and suppose 2 into c2 is new constant, say c2 dash. Therefore second solution is v equal to 2xy minus z square equal to c2 dash, and therefore the general solution is phi of uv equal to 0, where you must write what is u and v. U is x square minus y square minus z square, and v is 2xy minus z square equal to 0, and phi is an arbitrary function. So in this way, if it is possible to find out appropriate multipliers such that we obtain 0 in the denominator, then this will be easy to solve Lagrange linear or quasi-linear equation. So in this lecture we have explained how to select appropriate multipliers so that we obtain 0 in the denominator of new generated fraction, which we can use to find out the solutions of Lagrange auxiliary equations. Now every time it is not possible that we will obtain 0 in the denominator. So in those type of cases we have to think for another method or type. So that is our last type. If type 1, 2, 3 fails, then how to solve Lagrange auxiliary equations. So that we are going to discuss in upcoming lecture. So I hope you like this lecture. Thank you very much.